Hi, welcome to chapter 3, which is chapter 14 in your textbook. Yeah, page 179, kinetics of a particle, work and energy. So we're going to look at work and energy in this chapter. Yeah, so at the end, you'll be able to calculate the work of a force and apply the principle of work and energy to a particle system, to a particle or a system of particles. Remember, the first few chapters we only talk about particle, single particle. Yeah. After chapter 16, we will talk about a system which is comprised of many particles. Yeah. So for the time being, it's only a particle. Okay. So the application, roller coaster, like example, this roller coaster, it uses gravitational force to assist the car to reach the high speed in the valleys of the track. You can see, right, there is it's not motorized. It's like goes down, collects the energy, goes up, comes down, goes up. So that's how a roller coaster is being designed. So we have to calculate the energy here. Okay, another example is crash barrels. We have this only in US and probably Europe I didn't see, but much in US. Yeah. So these barrels absorb the car kinetic energy by deforming, so there won't be any much impact on the car. Yeah. Okay, so that is the reason for the barrel. So work and energy. So another equation for working kinetic problems involving particle. So involving the F equals to ma. Now, in the first chapter, just to recap what we have done, yeah, in the first chapter. What did we do in the first chapter? We found the formulas S, V, and A. Okay, that's the first chapter. The second chapter, what we did? We found the F equals to ma, right? Okay. Now, the third chapter, we're going to use this F here to find the work. Okay, work. So this is where we are at. Look, by substituting AT, V dVds into Ft equals to mat, the result is integrated to yield the equation which is principle of work and energy. So I'm not going to read line by line here. I'm just going to work straight to the formula. So there are few formulas, and okay, let me see. The lecture note is not too clear. I prefer to go to the textbook. I've sniped some information from the textbook. This is the same thing, yeah. So let's look at the textbook. Okay, so look at this. The first, you see, when you have to find, when you're given a question, yeah, there can be series of work due to, the first one is due to the variable force. Okay, so there is a variable force. So what is the formula? You remember, work equals to force times distance. Okay, so in this case, it is if a particle acted upon by a force undergoes a finite displacement, yeah, distance. Okay, so you just have to take force times distance. Okay, now why is it cos theta? Okay, sometimes what happens is that you don't have it in a straight line, so that's the reason why you have to multiply cos. Okay, example, yeah, this two is almost the same, yeah, this two is almost the same, yeah. Okay, let's say you have a box. Okay, you have a force, right? A force. Okay, what is work? Work is force times distance. If the force is a straight line, it's very easy. You take this force, you multiply with the distance or displacement that the box has moved. Simple. Okay, now of course you are an engineering student, they won't give as simple as that lah. So you have box, and now your force will be inclined, so you have an angle. So this force has to be parallel, yeah, parallel to this distance. This direction, force also has to be this direction. Okay, it cannot be perpendicular. So when you drop, you have what? F cos theta. Okay, ds, distance. So at the end of the day, it will look like something like this: force times distance times cos theta. Okay, can you understand? So that is the first formula. That is what is being explained here. Force times distance. Okay, settle. So this is also same, force times distance. Can you see that? Okay. Why is this U12? Because from the first situation to the second situation. Okay, from the initial to the final. 1 to 2 is final, initial to final. Why is it in integration? Sometimes this force is not a nice, beautiful fixed number. It can be like 8s plus 3. It can be something which is not constant. So that's the reason why you have integration. Okay. Okay. Next, we look at work because of weight. Yeah. So you know the formula mgh, right? Okay. Look at that and look at this. This is similar. Mg is weight. YH here is the delta Y. Why is it negative? Why is it negative? Yeah, why is it always negative? Because we are taking upward as positive. Okay, when you take delta Y upward as positive reference, and the gravity is actually always acting down, so that's why it's always negative. Okay, going back to the summary, so it will be the next line. Can you see? Okay, this is another box. So this box is actually available in your textbook itself. Yeah. Okay, you can have a look at it. So work because of weight. Yeah, mgh of negative mgh, or you can use negative w delta y. Okay, the next one would be work because of spring. When stretched or linear elastic spring develops a force which is F equals to Ks. K is the spring stiffness. Yeah, how hard is the how stiff or how hard or how strong is the spring. That is the K value. The bigger the K value, the stiffer the string. The smaller the K value, the softer the spring. Yeah. S would be the displacement from the unstretched position. Okay. Now, if you see here, okay, once again, this is also negative. Why is it negative? Because if you compress a spring, now the spring is in compression, where will the force be? The force will be opposing. Yeah. But when you stretch the spring, okay, where will the force be? The force will be opposing, trying to get back to its original. Yeah. So if you look at this formula, like what I've explained earlier, so we have the negative value. Yeah. So S2 square, S2 square minus with S1 square. Now remember, S is the displacement from the unstretched position. Yeah. Okay. So if you look at this, the summary that I have prepared. Yeah. So this is the box. So all this is actually available in the textbook. Yeah, I've just snapped it from the textbook just to share with you. Yeah, this is given you why is it negative. Yeah, so you can just read it. Okay, now just to continue. So spring forces. Okay, that's done. Principle, work and energy. You can just read it. Yeah, it's just reading. Okay, now work because of friction causing the slide. So friction is always negative. Okay, only happens if it's rough surface, and it's always a negative value. Yeah, so friction is given by the formula of mu n multiplied with the normal force multiplied with the distance. So if the question mentions about friction, then you have to put in friction formula in, and of course it is negative. Yeah. Okay, so now let's solve an example. Okay, as usual, I'm going to skip the example in this on the slide. So I'm going to go straight to the example in the textbook. Yeah, so I've sniped the example. So let's look at this good example. This example actually covers everything. Yeah. Okay. The 10 kilogram block shown in this figure, okay, rests on a smooth incline. If the spring is originally stretched 0.5 meter, so the spring is originally at 0.5 meter. Yeah. Determine the total work done by all the forces acting on the block when the horizontal force is 400. So you have an horizontal force pushes the block up the plane, which is S equals to 2 meters. So the distance it travels is actually 2 meters. Okay, it goes up 2 meters. So let's look at the formula that I have explained to you. So what we have here? We have this because there is an external force, and then of course weight. Yeah, we have that, and we have the spring, right? So we have all. So what we do, solve one by one. So first formula is UP, the horizontal force. So UP 400, force times distance. Yeah, distance. So what is the distance? The distance is, so you see the force is this way, right? The force is this way, right? So the distance has to also be this way. So what do you do? the distance, which is 2 meters, is actually along the slope. So you need to flatten the slope to follow this, to be parallel. So that's why it's 2 cos 30. Okay, you can understand? Okay, that's done. So that part done. So you get 692.8. Okay, next is the spring. So spring's formula is negative, always negative, half k is the spring constant, yeah, final s2 square. So what is the final length? We have 2 meters plus with the original, which is 0.5, yeah, because it's stretch 0.5. So 2.5 square minus with the initial, okay, half k s, and initial is 0.5. So you get negative 90. So you have two answers here already. Okay, next would be the weight. If you look, the box is actually having a mgh, right? So because it's from here, it's actually traveling up here. Vertical height will be from here to here. Okay, I repeat, yeah. See, the box is actually traveling from here, which is, this is the height, original height, to the new height here. So what is the distance here to here? It's 2 sine 30. So that's why it is mg 2 sine 30. Once again negative because the direction, because you're taking upward direction as positive, but the weight is actually negative downward. Okay, so you have the uw. So what is the total work done? You take this, you take this, and you take this, you add up, you get 505. Okay, so that's the end of the first video for chapter 14. Yeah, okay.